Okay, so when you read the problem, you should see that we have three different variables here. The number of acres of crop A, B, and C. We can call them apples, beans, and corn because it just kind of seems to go along with A, B, and C. And I've called these X1, X2, X3 because what if he added, I don't know, spinach? Then we'd be up to 4, and even if we used X, Y, Z here, then what would you do for the fourth one? Would you go to A? And then you're limited because of the slack variables, so that's why we use the subscripts. It's always important in the beginning of your problem to identify your variables. So the farmer's objective is to maximize his profit, and I've given you the objective function. Where do these numbers and the objective function come from? 100, 300, and 200 are what?
Acres. And the word number is acres, right?
It's how many acres that each crop should be planted to maximize.
If we read this part of the problem right here, there's our 100, 300, 200. So those numbers are the profit per acre of apples, beans, and corn. And of course our farmer wants to maximize his profit, and you as business professionals would be fantastic consultants for him. You know, maybe you know a farmer that you could help out. Not necessarily a farmer, you know, it could be a business application. And hopefully as we go through this problem, you'll see the business application of this simplex method and why it's so important. So we have some constraints based on acreage, money, and labor. He's only got 100 acres to plant his seeds on. So the amount of acres of crop A plus the number of acres of crop B plus the number of acres of crop C have to be less than or equal to the total acreage he has available on his farm to plant. And then he's only got so much money, and the apples cost him 40 bucks an acre for seeds, and the beans cost 20 bucks an acre, and the corn costs 30 bucks an acre. So when he buys all the seed, he can't use more money than what he has. So the monetary constraint cannot exceed his available funds. And finally, there are labor constraints. There's only 160 work days available to till, plant, treat, and harvest the crops. So perhaps this is in the Midwest, perhaps it's even a little bit further south with 160 work days. So we have that it takes one work day to do all those things, right? To till, to plant, to treat, to harvest. The beans take 2 work days and the corn takes 1 work day. So the total work days needed to grow and harvest all these crops has to be less than or equal to the available work days. Okay, so we've got 3 constraints, and when we put our objective function together with those constraints and give our non-negativity constraints, this right here is the formulation of the linear programming problem. So we maximize our objective function subject to the 3 constraints that we just discussed, and the farmer cannot plant a negative number of acres of any crop. He could decide, well, I don't want to do apples this year, so he could not plant apples. That would mean that he'd just be planting 0 acres of them. But that can never be negative. So we have to have our non-negativity constraints in this problem. And now, since you can't see all of this in the display, how many slack variables will this problem require? One for each constraint. How many slack variables will we need?
3.
3, exactly. So our initial system will take the first constraint and it'll add a U to change the less than or equal to sign into 100. And notice when I type this up, I left a whole bunch of space over here because I know I've got a couple more slack variables that are going to go in, as well as my objective function variable. The second constraint we're going to add our second slack variable of v to change the less than or equal to 3,200 into equals 3,200. In the third constraint, we'll have to add a third slack variable of w to change the less than or equal to 160 into equals 160. And then finally, the last part is to take all the variables on the right-hand side of the objective function and move them over to the left, changing the signs of all of them. So negative 100x1 minus 300x2 minus 200x3 plus p, the objective function variable stays positive, and then that whole equation is set equal to 0 because there's nothing left on the right-hand side. So can we formulate a tableau, an initial tableau from this? Brian, what does the first row look like?
1, 1, 1, 1, 0, 100.
Is there only 1 0 here? Like what about here and here?
Another 0 and then
2 more zeros? And then our vertical line and?
oh, because we had that to 0 for the p too.
Exactly, yes, so.
And then 100.
Right. Rodrigo, what would row 2 look like?
4, 20, 30, 0, 1, 0, 0, 32.
Fantastic. And Alfonso, row 3?
1, 2, 1, 0, 0, 1, 0, and 6, 160.
Very good. And then we generally draw a dashed line to separate our constraints from the objective function representation. So, Jenny, can you tell me what should I put in for the last row?
Negative 100,
Yes?
negative 300,
Mm-hmm.
negative 200,
Mm-hmm.
0, 0, 0, 0.
What goes in here?
1,
Yep.
and a 0.
Fantastic. So I'm not sure if it would help you to put in the zeros to hold the places. Or if it would help you more to label your columns. Or both. But whatever works for you, use that method. Now, of course, when I wrote the non-negativity constraints, those just transfer over. I don't change those inequalities to zeros. And notice I've added the slack variables to the list. The slack variables will never be negative. Okay, so here's our initial simplex tableau. Do we have any negatives in the bottom row? Okay, so that means we're not at the answer yet. What is the most negative value? Negative 300. So that identifies our pivot column is column 2. And now the next step is to take what? Right-hand side. So 100 divided by what? Okay, and then the next one? Which is 160, yes. And the next one? 160 divided by 2. 160. pivot about the 2, this should be the next tableau that you get. Please tell me if that's what you got.
What's that pivot row? Which one was that pivot row?
The row was 3,
3, and then column 2.
yes. Did you get it?
I'll go to the program and check it
So this is what you should get. Let me know if you get this.
So that should just be 1,600, that's not actually 1.6.
Oh, yes, thank you for identifying yet another one of my typos. Yes, that's
That's okay, I just wanted to make sure.
1,600. So did you get that?
Yes.
Fantastic. Are we done yet? No, why not?
Negative.
There's still a negative in the bottom row. So, because there's still a negative in the bottom row, that identifies my pivot column as column 1, 2, 3. And then I have to take the right-hand side values and divide them by the values in the pivot column. So 20 divided by half is 40. 1,600 divided by 20, 80. And 80 divided by half is 160. And I want the smallest quotient here, which is the 40. So that identifies row 1 as my pivot row. So I want to pivot column 3, row 1, or row 1, column 3. So once again, that would take 4 row operations if you were doing this by hand. If you were doing it on the calculator, it only requires you to run the program. And select the correct row and column. Okay, so when you run that program one more time, you should get this tableau here. Is this what you got? Fantastic. Are we done yet? Even better, right? So we need to identify the solution. So it's helpful to have our columns labeled. So we had 3 variables, 3 slack variables, the objective function, and the right-hand side. So is x1 a unit column? Is there 1, 1, and everything else in that column are zeros? No, so x1 is not a unit column. Whenever we have not a unit column, that means our variable is equal to 0. Is x2 a unit column? Yes, it is. So we take the one in that column and we want to connect it to the value on the right-hand side. So that means x2 is equal to 60. Is x3 a unit column?
Yes.
Yes, so what is its value? 40, right? x3 is 40. Is u a unit column?
No.
No, so what's the value of u?
0.
What about v?
Yes.
It's a unit column, so it's
800.
800. What about w?
No.
Not a unit column, so it's 0. And then let's put p at the front because that's what we wanted to maximize. Is p a unit column? Kind of has to be, doesn't it? So what this problem, or the simplex method, tells us when applied to this problem is that the farmer can make a maximum profit of $26,000 when he plants none of crop A, so that means no apples, 60 acres of crop B, or beans, and 40 acres of crop C, or corn. And he's got a slack variable there. Could you look back to when we defined the constraints and see which one we had to add V for? Which one of these constraints did we add V to?
Crop B, right? Or the second one.
The monetary constraint, exactly. That's where we had to add our slack variable of V. So the fact that we have V, our slack variable being 800, means that the farmer's got extra money left over. He didn't have to spend all his money on seed. If you were to plug in these three values into the monetary constraint, you would see he's not spending the full $3,200 that he has to spend on seed, but only spending $2,400 of it. So not only are you telling the farmer how much he can make his profit, you can also tell him how to save money in the meantime. So I think this is an excellent example demonstrating the simplex method.